Imagine a pristine, perfectly organized room. Every item is in its place and there's a sense of calm and order. Over time, dust settles, things get misplaced, and disorder naturally increases. This gradual shift from order to chaos is inevitable. This tendency towards disorder is what physicists call entropy. It's a measure of randomness or unpredictability in a system. It's a fundamental concept woven into the very fabric of our universe, influencing everything from the smallest particles to the largest cosmic structures. The second law of thermodynamics elegantly captures this principle. Entropy in an isolated system can only increase over time. This law governs the direction of natural processes. In simpler terms, things tend to go from order to disorder, from structure to chaos. It's a universal trend that we observe in everyday life. Think of a sandcastle on a beach. Wind and waves inevitably dismantle its intricate design, scattering sand grains into a state of greater randomness. This is entropy in action. Entropy isn't just limited to our physical surroundings, it pervades the cosmos. From the formation of stars to the expansion of galaxies, entropy is at play. Stars burn through their fuel, radiating energy and increasing the entropy of the universe. This process is a key driver of cosmic evolution. Black holes, those cosmic behemoths, are thought to be the ultimate entropy sinks, where order seemingly vanishes. They represent the extreme end of entropy. Understanding entropy is crucial for comprehending the flow of time, the fate of the universe, and the limits of what's physically possible. It shapes our understanding of reality. It's a concept that bridges the microscopic world of atoms and molecules to the grandest scales of the cosmos. Entropy connects the very small with the very large, providing a unified view of nature. Imagine a box divided into two compartments with a tiny hole connecting them. This setup will help us understand a fundamental concept in thermodynamics. One compartment is filled with gas molecules while the other is empty. Initially, the molecules are confined to one side, creating a state of order. As time passes, the gas molecules, in their constant chaotic motion, will inevitably pass through the hole and distribute themselves evenly between the two compartments. This movement is driven by their kinetic energy. This simple visualization beautifully illustrates entropy in action. Entropy is a measure of disorder or randomness in a system. Initially, the system is in a state of low entropy. The gas molecules are confined to one side, representing a degree of order. This ordered state is less probable. As the molecules spread out, the system's entropy increases, reflecting a more disordered and random arrangement. This transition to higher entropy is a natural progression. It's highly improbable, bordering on impossible, for the gas molecules to spontaneously gather back into one compartment. Such an event would defy the principles of entropy. Entropy dictates that systems naturally evolve towards states of higher probability, which often correspond to greater disorder. This is a fundamental principle of the second law of thermodynamics. This principle extends beyond gas molecules. It applies to various natural processes. Think of a drop of ink diffusing in water, where the ink molecules spread out to achieve a uniform distribution, or heat flowing from a hot object to a cold one, until thermal equilibrium is reached, or even the shuffling of a deck of cards, where the order of the cards becomes more random with each shuffle. All these processes demonstrate entropy's unwavering tendency to increase disorder over time. This universal tendency is a cornerstone of understanding the natural world. In the 19th century, James Clerk Maxwell, a brilliant Scottish physicist, proposed a thought experiment that seemed to defy the second law of thermodynamics. This law, a cornerstone of physics, states that the total entropy of an isolated system can never decrease over time. Imagine a tiny, intelligent being, Maxwell's demon, controlling a small door between two compartments of gas molecules. This hypothetical creature has the ability to manipulate the movement of molecules in a way that seems almost magical. This demon possesses an uncanny ability to track the speed and direction of individual molecules. It can distinguish between fast-moving and slow-moving molecules with incredible precision. By selectively opening and closing the door, the demon could, in theory, separate fast-moving molecules from slow ones, creating a temperature difference between the compartments. This would result in one compartment heating up while the other cools down. This separation of temperature seems to violate the second law, which dictates that heat cannot flow spontaneously from a cold to a hot reservoir. The law implies that energy will always spread out evenly if left to its own devices. However, the resolution to this paradox lies in the demon's need for information. The act of gathering and processing this information is not without consequence. To operate the door effectively, the demon must acquire knowledge about the molecule's speeds and positions. This process of acquiring information is crucial to the demon's operation. This acquisition of information, it turns out, comes at a cost, increasing entropy elsewhere in the system. The energy expended in measuring and sorting the molecules compensates for the apparent decrease in entropy. Maxwell's demon, though a thought experiment, highlights a crucial point. The second law of thermodynamics remains undefeated. The law holds true even in scenarios that initially seem to challenge it. Even seemingly paradoxical scenarios ultimately reveal the subtle ways in which entropy always increases even if it's not immediately apparent. The universe, in its complexity, always adheres to this fundamental principle. Section 4. Quantum Quirks, Exploring Reversible Computation and Entropy. The quantum world, with its bizarre and counterintuitive rules, offers intriguing perspectives on entropy. One such concept is reversible computation, a theoretical model of computing where operations are performed in a way that doesn't increase entropy. In classical computing, every logical operation generates heat, a form of energy dissipation that increases entropy. Reversible computation, however, proposes a way to perform computations without generating any heat, thereby preserving information and not increasing entropy. This idea has profound implications for the relationship between information and entropy. If information is indeed physical, as some physicists believe, then reversible computation suggests that information itself might be subject to the laws of thermodynamics. While practical reversible computers remain a distant dream, the concept challenges our understanding of entropy and its relationship to information processing. It hints at a deeper connection between physics and information than previously imagined. Section 5. Black hole enigma, Hawking radiation and entropy's role. Black holes, those enigmatic cosmic objects with gravitational pulls so strong that not even light can escape, present a fascinating case study in entropy. They were once thought to be the ultimate entropy sinks, where information and order vanished irrevocably. However, in the 1970s, Stephen Hawking proposed a revolutionary idea: black holes aren't entirely black after all. Due to quantum mechanical effects near the event horizon, the point of no return around a black hole, they emit a faint thermal radiation now known as Hawking radiation. This radiation carries away energy from the black hole, causing it to slowly evaporate over time. More importantly, Hawking radiation carries entropy as well, suggesting that black holes aren't the entropy dead ends they were once thought to be. The study of black holes and Hawking radiation continues to challenge our understanding of entropy and its role in the universe. It highlights the interconnectedness of gravity, quantum mechanics, and thermodynamics, pushing the boundaries of our knowledge about the cosmos.